So with a tiny delay, we have our second speaker of the first day, Joonkyung Lee from Hanyang University, telling us something about the commonality of graphs. Okay.
Right. Thank you for the introduction and the invitation as well. It's my pleasure to give an online talk here. So I'm going to talk about some extended commonality of cycles and paths via Schur convexity. This is a joint work with Jang-Soo Kim, who's an algebraic combinatorialist in Sungkyunkwan University in Korea. Yes, so let me start with something that all of you would know. So first, Ramses Theorem. So in its pure qualitative statement, Ramses Theorem states that given any t, you can find some large enough n such that any two-edge coloring of Kn contains a monochromatic copy of Kt. Okay, that's obvious. And as a consequence, if I fix my h, oops, this looks weird. So fix h, and this fix h such that you have the number of vertices at most t. Then, as a consequence, what happens is given any two-edge coloring of the same Kn also contains a monochromatic copy of H. Right? Yeah, so this opens up. Is there an echo here? Maybe I should turn my... I didn't turn anything on. Okay. Okay, so if this is fine, then I'll continue. Yeah, so the next natural question is then, how many? So how many monochromatic copies of H are there in a two-edge coloring of Kn? So here, the question is how many we can guarantee. So let me just define the Ramsey multiplicity constant in a kind of rough way. So it's a limit of when n tends to infinity, we consider the minimum number of normalized copies. Minimum normalized, maybe normalized number of copies of monochromatic H. Monochromatic. Yeah, and we take the limit, and yeah, this is the Ramsey multiplicity constant. I mean, let's skip very detailed definitions. Just let's just keep it soft. And we say that H is common if this Ramsey multiplicity constant is exactly 2 to the 1 minus the number of edges in H. So here E of H throughout this talk denotes the number of edges in H. Okay. Yeah, if this is true, then we say that a graph H is common. And here's a remark. So the Ramsey multiplicity constant is always at most 2 to the 1 minus the number of edges in H because of the random coloring. Random two-edge coloring, of course. So what do I mean by random coloring? I just flip a coin, and then I just flip a coin to decide whether to put red or blue to each edge. Okay. Yeah, then by some easy consequence of concentration inequalities, you can easily say that this bound here, 2 to the 1 minus the the 1 minus number of edges in H is attainable by these random 2-edge coloring, and hence the minimum is always smaller than this. And H is common if this is really the minimum number of monochromatic H in any coloring of H. Okay, so this is a basic setup. Many of you would be familiar with these basics of graph Ramses theory. And here's a brief historical overview. So the first example of common graphs is by Goodman. So Goodman's formula essentially states that a triangle is common. Yeah, so this is an easy consequence of Goodman's formula. And this Goodman's formula was actually a very important ingredient in proving Thomasson's bound on the diagonal Ramsey number, R of t being at most 4 to the t divided by t. Yeah, so this was a key ingredient in Thomasson's bound, later improved by David Conlon and recently by Ashwin Sa. But having seen these examples, so this was only 80s. So having seen these examples, this example, Erdős actually wondered if we can refine this commonality of a triangle to cliques to apply further in this asymptotics of the asymptotic estimates of the diagonal Ramsey numbers. So the Erdős conjecture here states that every KT is common. So here KT means, of course, a complete graph on T vertices. And for Burr and Rosta later conjecture that any fixed graph H is common. So these conjectures were made during 80s or late 70s. And then, and these famous conjectures were both disproved by Thomasson and by Sidorenko, respectively. So Thomasson disproved Erdős conjecture, which is a weaker statement than the Burr-Rosta conjecture. So what Thomasson proved is any KT is uncommon for any T at least 4. Yeah, so somehow the edges and triangles were special. So any clique larger than these two are uncommon, which means there are worse examples than the random coloring, so which avoids making too many monochromatic copies of a clique. And at roughly the same time, Sidorenko also proved that this graph, the triangle plus a pendant edge, is uncommon. So which disproves the Burr and Rosta conjecture. And later on, worse and worse counterexamples were found. So Jäger, Stobicek, and Thomasson in late 90s proved that any graph that contains K4 is uncommon. So this generalizes Thomasson's results. And so the clique number here matters. So whenever your graph contains K4, then it is uncommon. And one of the earliest paper by Jacob Fox states that actually the Ramsey multiplicity constant can be exponentially smaller. Exponentially smaller than this. Then the commonality bound. If you cook up some H that is non-bipartite. So yeah, these were some typical examples. I mean, there are many other papers concerning the commonality, but this is a very brief overview in the history of the history. So then you might wonder, well, then what graphs are common? If the common graphs are so rare, then what graphs are actually common? Well, there are many examples. So the bipartite case entirely relies on the famous conjecture of Sidorenko. So, yes, so far, all the known examples for bipartite common graphs satisfy Sidorenko's conjecture, and it is an easy consequence of the Sidorenko's conjecture itself that any graph that satisfies, any bipartite graph that satisfies Sidorenko's conjecture is common. Yeah, so it entirely relies on the progress on Sidorenko's conjecture, but this is a major open problem. So we don't know if the two problems are different, like determining the bipartite common graphs or Sidorenko's conjecture are different. Of course, Sidorenko's conjecture implies that every bipartite graph is common, but we don't know that yet, right? Yeah, so this is bipartite case and non-bipartite case, which is kind of complicated to recall because there are various results. But one of the cornerstones among these lots of results is by Sidorenko in the same paper as here, where he disproved the Burr-Roster conjecture, states that any odd cycle are common. Yeah, and of course there are many results. There are other examples of common graphs found by Yegor, Stobicek, and Thomason, for example, and there are other examples found recently by Jessic, myself, Lidicki, and Volets, and there is a recent breakthrough by Dan Kroll, Volets, and Wei, obtaining a infinite, so unbounded chromatic number. So what's the result? So common graphs with unbounded chromatic number and so on. So so we focused in this paper, we focused on the tripartite case, and they actually constructed there are common graphs with unbounded chromatic number and so on. But let me focus on cycles and path for this talk. Okay, so this is a very brief historical overview on the topic. And let me move on to the next topic, which is the complete homogeneous symmetric polynomials. So here's a disclaimer. So here, the disclaimer being, I'm no expert in this topic. Yeah, so I'm no expert in the theory of symmetric polynomials. But I mean, it's a central topic in algebraic combinatorics. So let me just define what complete homogeneous symmetric polynomial is. So here D means the degree. It's homogeneous polynomial, so it's degree D. And I've got k variables, x1 up to xk. And then I look at all the non-negative integer solutions of d1 up to dk, whose sum is d. Okay. And then for each of these solutions, non-negative integer solutions for d1 plus d2 plus up to dk being d, I just assign the monomial x1 to d1, x to the d2, xk to dk. Yeah, so this is the very definition of complete homogeneous symmetric polynomials. And this is a very well-known symmetric function with useful properties. For example, it's non-negative. So when the homogeneous degree is even, then it's, yeah, the whole function is non-negative for the entire entire domain of the RK. Okay, so this is non-negativity, which is useful. And the second being the Schur convexity. So here I wrote a consequence of Schur convexity because it takes, it takes 1 minute or two to define it very precisely. And I think this version is kind of enough to understand what it means in a very roughly. Yeah, so it states that whenever I take the even degree polynomial here, even degree complete homogeneous symmetric polynomial up to x1 up to xk, and here I plug in x bar, which is the average of x1 up to xk. Okay, and then this consequence of Schur convexity states that when I take the average of these k variables, my function gets smaller. So that's the Schur convexity. Okay, and yeah, so far I explained two distinct topics. One, Ramsey multiplicity. Two, complete homogeneous symmetric polynomials. So these sound very like distant, right? But the beauty here is that we actually connect these two seemingly distant areas, the algebraic combinatorics that concerns with symmetric polynomials, and on one hand we have extremal combinatorics that concerns with the minimum number of certain discrete structures. Okay, so just to see how they connect, let me explain some amount of proof techniques when we prove some graph is common. So it is convenient to use graphons, the dense graph limit, which is a symmetric function from the 0, 1 square to 0, 1. So this is a very standard argument, so which is symmetric. So symmetric here means wxy is same as wyx. So this is a very standard dense graph limit, which means we can basically replace our large graph when n gets larger. Whenever your sequence of graphs is dense and you want to count some small number of, you want to count a fixed graph therein. Okay, so for example, if I want to count the number of normalized triangles, so this is triangle, and then I can just express it in terms of the expectation of wxy, wyz, and wzx. Yeah. So what does it mean? So I sample each vertex x, y, and z independently at random from my vertex set, and I'm interested in their connectivity in this large graph W, or the graphon W. So here I've got x and y, and z and x. And what I want is all of these edges exist in a large graph so that I have a triangle like this. So if I replace the existence of each edge by a indicator function gxy, say, then I will have something like this. And as a natural generalization of these indicator 0, 1 indicators in a weighted setting, I have this expression over here. So it's nothing but an integration of something that represents a triangle. Okay, so in this language, H being common is equivalent to the normalized density in W and the normalized density in 1 minus W. So what are these? So if my W stands for the red graph in my Kn. And 1 minus W is simply its complement, right? So this is the blue graph. And then the commonality is equivalent to say that my normalized H count and my normalized H count in red and blue graphs is actually at least 1 minus 2 to the 1 minus the number of edges in H. Yeah, so this simple inequality is actually equivalent to H being common. And in this language, if I restate the classical formula of Goodman, then this is simply the triangle count plus the triangle count in 1 minus W is 2 to the 1 minus what? There are 3 edges, right? So that's a quarter. Okay, yeah, so this is a statement. So to prove this, let me just reparameterize these functions a little bit. So if I let my U be 2 times W minus 1, then what happens is my W is 1 plus U over 2, right? And then 1 minus W is, 1 minus W is 1 minus U over 2, okay? And then what I can do is to plug this into here, the formula that I want to average over, right? And then what I get is, well, I can just simply expand these out, right? I can just simply expand these out to get 8 terms, right? And let me just pull out the 1/8. And then what I have is 1, which comes from choosing 1, 1, and 1, and some linear terms that looks like uxy, uyz, uzx, and some quadratic terms such as uxy, uyz, and so on. And the cubic term at last, the product of the 3. Okay, so these are quadratic part, and this is cubic. Okay, and these are linear. Okay, so this is a very standard expansion that you can see just everywhere, basically, in the theory of graph limits. And if I do the same thing with a slightly different function, 1 minus W, then what I get is basically all these signs here just flips. And then what happens is this is 1/8, 1 minus linear terms plus quadratic terms, because, I mean, for obvious reasons, and minus cubic terms. Yeah, so this is what I get. So what happens if I add these two? So linear terms cancel off, and cubic terms also cancel off. Okay, so what I have is 1/8 times 2 plus 2 times the quadratic terms. Okay, and hence, if I calculate this quantity, the triangle count in W and the triangle count in 1 minus W minus 1/4, then it's simply a quarter times the average of the quadratic terms. Typically, this includes the expectation of Wxy and Wyz, which you can easily prove that it's non-negative. Yeah, just to illustrate the trick, you just integrate this expectation by x first and then z, then it just becomes a square. Yeah. Okay, and hence this is non-negative, and hence we prove Goodman's formula. Okay, so this is a proof. Right. And let me move on to a generalized proposition, which is rather classical one. So H is common if and only if we do the same trick, same substitution, here I do W equals 1 plus, W equals 1 plus U over 2, okay? So that's a trick. And then in every expansion, what remains is the even subgraphs of H. And then I look at the TF of U, which is the average of the even terms. And then I want this to be non-negative, just like I did for the Goodman's formula. And this must happen for U from which has the range from -1 to 1. So here, because of the substitution, so my U ranges from -1 to 1 rather than 0 to 1. Yeah, it should be stupid if my U is non-negative. This is just a non-negative sums, right? So yeah, as a natural generalization of this argument, what I get is H is common if and only if this part is non-negative. Okay, then let's do an example. So what are even subgraphs of an M edge? So let's say there are M edges, which I call PM. And then what are the even subgraphs of these? Okay, so it's kind of complicated, but we can look at those subgraphs with exactly 2 edges, which is the easiest part for the even subgraphs with positive number of edges, right? So if I do it correctly, then what I can do is, so it's either a 2-edge star, a path of length 2, or just a matching of size 2, okay? So how do I do this? Well, here, if I choose a central vertex for a star, which has n-1 choices, right? Then, so yeah, then I have n-1 2-edge stars, right? So I choose this or this or this, and that's exactly, there are n-1 choices for this. And the rest, so this is actually, so m choose 2 minus n-1, right? So this is exactly the number of matchings, because I just exclude these from the m choose 2, which is n-1 choose 2. So this is n-1 choose 2. Okay, so this is one example. So we just sum up all these terms. There are higher terms like 4-edge subgraphs, 6-edge subgraphs, which is quite complicated, even for this easiest case, which is a path, right? And here's a lemma using a spectral argument. This is originally by Gotzel and written down by Erbish and Shimonovitz in their old papers. So it's a basic linear algebra, so it doesn't really matter, I think. So it's a four-color lemma saying for every U that is of this range, say, we can connect its path count to a random variable, a mth power of a random variable. So what's the random variable here? Its range is simply the eigenvalues of U. Okay, and basically says that this is a convex combinations of the random convex combination of the mth powers of the eigenvalue, and hence I can just translate that back to a random variable, which is a necessary interpretation in our purposes. Okay, so what happens here is a simple corollary. If I look at the 2-edge case only, then what happens is this times n-1 plus that times n-1 choose 2. And this exactly corresponds to this case. So what's this? This is h2 of x1 up to xn minus 1. So what does that mean? So what I'm going to do is to choose my d1 plus d2 up to d n minus 1, which sums up to 2. Okay. And then I look at x1 to the d1, x to d2, and x to the n minus 1, dn minus 1. What does that mean? Well, this is a quadratic polynomial, nothing serious here. Everything's quadratic. So every variable is either quadratic, just by itself, some xi squared, or xi times xj. So xi squared terms correspond to this case. Well, I shouldn't really erase it. So x squared term corresponds to this case, and the different variables correspond to the other case. And yeah, and their numbers are exactly corresponding to each other. And our key observation here is that this is not a coincidence. So here's a theorem by myself with Zhangxu, which states that if I look at any even subgraphs of fixed size, let's say 2D, then it translates back to a complete homogeneous polynomial with some exact k values, so it's an exact number of variables. Yeah, this is a beautiful, beautiful correspondence, right? And let me just give you some idea why this works. So the correspondence between the two is just by a very simple one-to-one correspondence. So here I have an example. So if I were to count a 4-edge subgraphs in an 8-edge path, and then my k is 5 due to this calculus here. Okay, and then what I'm going to do is to look at some imaginary edges, not really imaginary, but look at the complement of f. Okay, so here E1, E2, E3, and E4. And I add one imaginary edge, E5, at the very end. And what I'm going to do is to look at the leftmost vertex of each E, which I marked like gray here. Okay. And then I look at the component of f that includes this vertex over here. Then what I have is my d1 is 0. So that's the size of the component of f that contains the left vertex of E1. And if I look at E2, well, then this is my vertex. And the component of f that contains this guy is 1. And so on. So the component contains this guy is of size 1. So this is the number, and so on. So here, the last component is of size 2. So this is my number. And that exactly corresponds to an non-negative integer solutions for this. Yeah, and this is precisely the correspondence. Okay, so how much time do I have? Maybe 10 minutes? Only 1 minute. Okay. Okay, let me finish off quite quickly. Okay, so you've seen the key observation. So here's a Hunter's theorem in 1977 saying that this is simply non-negative. Yeah, so that I can just look at here and everything's non-negative. So basically, if I fix a even size, then that's non-negative. So it's a sum of some non-negative terms, and hence non-negative. And hence what we prove is a generalized inequality, not only for the graphons W, but also for generalized kernels, just whose domain is just R. Okay, and this inequality holds for any H that is a path or a cycle. And this answers a question of Sidorenko, who proved this the same inequality for the kernels for even length paths to prove commonality of odd cycles. Okay, so this is one application, and if I apply the more advanced Schur convexity of the complete homogeneous symmetric polynomials, then what I get is the following inequality. So here I replace the bound, the constant bound, by some convex combinations of the by a convex function of the H densities. And then this inequality holds for H being path or sidepose, and this confirms a recent conjecture of Behaig, Morrison, and Noel. And yeah, to just recall, the Schur convexity is like this, and this part over here almost exactly corresponds to the H density bound. Okay, so yeah, I'll stop here.
Let's thank Joonkyung